So we'll get started. This is our first official class. A couple, first I'll just kind of go through some of the general business. This will be a bit of a review if you were watching last Friday or saw that video, but I just want to make sure everyone's on the same page so I can address questions if you have them. We do have a problem set due on Wednesday. This will be due to Gradescope. So there are two main documents on Canvas which you should look at. One is just general updates to the class. This has a lot more detailed information of kind of what this sort of these two update slides have. Hopefully answers questions. If you have additional questions, send me an email and I can provide more feedback. And I can update those documents as well if since other people may have the same questions. And I'm going to say Wednesday before class, our normal class time, just so that our TAs will have the rest of the day to grade them, and also Thursday so we can get them back to you on Friday to review them. So sort of similar to our normal schedule. We're still a little uncertain how long it'll take us to grade in this format, so we'd like to get an early start if possible. There is an updated version of Problem Set 4. Content has not changed. There's just boxes for you to write in answers that will let us grade things on Gradescope a little bit more easily. So if you've written on a different type of document or a different format, please follow the Problem Set 4. Since we lose 3 classes, I shortened Topic 6. That has now been uploaded as Lecture 26 on YouTube. Hopefully people have links to that on the slides that I've been putting online into Canvas that cover sort of the notes written out. There's a link at the very top that should take you to that playlist. Alternatively, if you just save, I think, my channel webpage, you can get to all the playlists as they update. And the only immediate impact this has on you guys is Problem Set 4, Question 6. You won't learn how to do, so you can just put A for the answer. According with this, I have updated the syllabus and course calendar with some of the right dates and times for the exams and whatnot. I put up a practice exam 4 that you should be able to see. And I also added in a reaction summary and synthesis strategy for topics 5 and 6. So this should give you new combinations of reducing agents with different reactants, in addition to some ways of thinking about how to make amines. And also I filled in the sort of big interconnecting flow chart that we had earlier in this at the beginning of topic 5 for interconversions of many different functional groups. Oh, and on the Gradescope guide on how to upload files, if you're uploading or writing directly onto blank sheets of paper, this gives you a general process of, I think, how you should attempt to fill it out. I know this still won't be perfect, but if you get us in generally the right ideas, I think Gradescope will be able to pick up the answer, and this will reduce the amount of work on our end to get these things back to you quickly. The formats for exam 4 and 5, we won't be merging them. I decided, well, turns out that my initial plan was against GT policy for the changes. So we're going to just have 2 exams with less content. They will be in 1 week, and the next one will be on April 17th. We're going to be doing these the same way that we do the problem sets, where you will be able to write on a sheet of paper, print something out, or fill it out on a tablet and upload it. I've designed them to be about 5 minutes shorter, and I'm giving you guys a bit more time overall so that you can, I think 65 minutes in total, so that you can have time to print, upload, however you need to use this time to get it to Gradescope. This seems to be an acceptable amount of time. If you're in a different time zone and the time frames need to be changed, just let me know. I can document this, and then we can work out a system for you to get the exams as well. The exams will be released on Canvas, so there's a way I can time that for people so that you can see the exam during a certain window. If you previously were testing in the testing center, this won't impact you. You'll still be able to submit exams after the technical deadline, so you'll just submit them whenever is appropriate, and we'll go from there. And I'll also be uploading what I say is sort of a skeleton of an exam. This is essentially the way the exam will be laid out on a sheet of paper with just no questions. That way you can at least anticipate where questions will be and how will be laid out. If you're either wanting to print this out ahead of time to write in directly, that should save you some time so that it's a bit more balanced with people who are using something like a tablet. And if you are using a sheet of paper, you could sort of prepare your sheets of paper ahead of time so you know where you'll be writing in answers. You're not trying to stress over things being in the right place whenever you're in the test itself. Cool. So are there any questions right now about sort of this process that I can address at the moment? I'm going to go with a no. So we've overall actually we have, I guess, two different YouTube videos. People I believe have been going and watching them to some extent. And I'll click on one. Let me see how many, if it'll show me how many views it has. For one of the newer ones, oh well, that's the wrong one. Actually, I've updated 3 videos total. Sorry, because I added in a bonus one that are just to get ahead. Are resubmissions allowed for the exam on Canvas? What do you mean by resubmission? I'm not sure, because the exams will be submitted on Gradescope, because that's where we need to submit it in order for it to be uploaded. Oh yeah. Oh yeah, I believe that is the case. I have never, because I will actually make it just like an assignment, and assignments can be uploaded and erased again. Yeah, so I think that should be possible. I guess the timing of that might, if you're going to submit something, you're actively submitting it, and you notice a mistake, um, that might require you to do some more changes. But the way that it's set up, it's actually technically going to be called an assignment just with the title exam 4, so you should be able to upload that again. So today, if we can, I'd like to focus on maybe lecture 25 and 26. There is a lecture 27 video that will not actually be covered on exam 4, but we're just getting ahead a little bit so we can start to have a bit more material for exam 5. One thing I do want to note is that on the lecture 26, I didn't include one of these sort of news and update slides, and I meant to do that. So if you want to go see a sort of summary of lecture 25, I put it in there. I also added in this piece of information, which I can go over in a second, that'll be of relevance for your problem set. But mainly this lecture was all about amines. We pretty much started and finished the topic. We talked about some things like nomenclature, but we don't really cover that in this class. We reviewed some ideas about acid-base chemistry of amines. This is similar to some of the ideas that we had for 1 second. I will address that very soon, Matt, about the exam 4. Acid-base chemistry, which I think utilizes some concepts from topic 1. Then we learned reactions of how they react with alkyl halides. That's just hard to control the number of alkylation events that take place. The synthesis of primary amines. So this is the Gabriel synthesis, reduction of azides and oximes were the new ways to make primary amines. We learned something called reductive amination, which is shown here. And this is good for making secondary and tertiary amines. Note that we have a new reagent. This is sodium cyanoborohydride. It's a weak reducing agent. It's even weaker than sodium borohydride because there's this nitrile on the group that is an electron withdrawing group. And the only thing it can really react with is iminiums. So we really need to have this positive charge here. The positive is important. Oh, that's horrible writing. And then we can selectively make amines this way. The last thing we learned is the Curtius rearrangement. Old Theodore Curtius. And it does this wacky rearrangement where we turn an acid chloride into an isocyanate. So the main thing to look at here is that we have a carbon that used to be here, and now it becomes a nitrogen due to this 1-2 shift that takes place with loss of nitrogen, where the electrons from the oxygen are able to come down, sort of push this group over onto the nitrogen to kick out nitrogen gas. So to answer Matt's question, I had the next class not being an exam 4 review because I kind of wanted to do that after we turned back the problem set. For this week, if people want to continue to ask questions over sort of both materials on Wednesday, I'd be fine with that. I just wanted to make sure there was still a little bit more time on Friday to cover and review for the exam, since the exam's actually on Monday. So this is sort of an awkward period of time where we have a lecture appear before exam 4 where it's not covered. But I'm pretty open to the format. I think we should have plenty of time for the remainder of the classes to answer questions during the class to hopefully give some feedback. But yeah, this is the main thing you may want to note. Sodium borohydride is able to reduce anhydrides. So these are not esters. These are anhydrides because we have 2 electron withdrawing groups on the oxygen. Sodium borohydride is able to attack the anhydride and then kick out a carboxylate leaving group. And then this aldehyde can be further reduced again. So this is something that you will see on the problem set. So it's not that the carbon is lost, the carbon gets shifted. The carbon ends up appearing right here. So a lot of times when people do a Curtius rearrangement, so now the carbon is on the other side of the nitrogen, but when people do the Curtius rearrangement, they frequently will add water, and water will hydrolyze isocyanates to a primary amine. So it's kind of like you turned an acid chloride into an amine and you lose this carbon along the way. A lot of people do the Curtius rearrangement without taking this carbon away, but it always gets moved to first an isocyanate. So overall, going from here to here, you lose a carbon. This is something that people frequently would sort of mess up in prior classes. I've tried to get it a bit more clear that nitriles will add 1 carbon, Curtius removes 1 carbon, and something like a Gabriel synthesis will keep the same number. You should get some feedback. The way it works is we have sort of, whenever we give these solutions back, it should appear to you in the form of a rubric where we show kind of how we graded it. And I think it should be sufficiently detailed so you'll be able to see what you missed and the score you received for that problem. I think they can add in extra notes. Again, we still need to, we don't know how long it will take for us or how detailed all this information coming back to you will be, but I will post a video that will kind of go through all the different solutions, and you guys can ask specific questions if you have them as to kind of what went wrong. But you should have a score and feedback through Gradescope by Friday. That is my ambition. So to answer Madison's question down here on the anhydride reduction, sodium borohydride never reduces carboxylic acids, so it will still never reduce a carboxylic acid. If this were lithium aluminum hydride, then you would be able to reduce both of them at the same time. Yeah. And so on the reaction summaries the reaction summaries that I put on Canvas, this should be on that grid. All the new ones are highlighted in yellow. So if you're looking at functional group compatibility, or it's like, does this reagent reduce this type of functional group, that should help you out along the way. Cool. All right, so first I'm going to answer the question that someone had on Piazza. It was about this problem on the lecture notes, where we had 3 different amines, and we're trying to rationalize, I changed the question slightly during the lecture where I said, instead of saying pKa, since these terms are sort of vague on how people use them, let's say, um, let's say increasing basicity. So we want to order them in which one is the most basic, which one is the least basic, and how can we rationalize this? And the factors we want to think about that contribute to both nucleophilicity and basicity frequently will be things like hybridization, different maybe electronic effects, or potentially resonance effects, with the most substantial resonance effect being aromaticity. There is some overlap in some of these ideas because if you have a nitrogen in resonance, it probably does change its hybridization. But first we want to look probably at hybridization first. We want to see what is the hybridization state of each of these nitrogen atoms. So nitrogens that are have more S character will be more electronegative, so they really want to hold on to their lone pairs. So each of these nitrogens have a lone pair, and this is the basic component of any of these amines. So if we go through, we start with pyrrole. This nitrogen is going to be sp2 hybridized. That's because it's participating in resonance. So it's a 6-pi aromatic system. So this lone pair will go purely into a p orbital to communicate with the other pi bonds and make an aromatic system. The pyridine ring in the middle, this doesn't have any resonance possibilities. It just has simple sigma bonds. So this will be sp3 hybridized. And here we see this nitrogen in pyridine has a double bond and a single sigma bond. So this is a classical sp2 structure. So going straight from hybridization, actually that's all that we really need to know in order to determine that the middle structure will be the most basic. And I think this is where the question came from. So one of the leading effects or things that will actually cause amines to be the most basic is essentially to have alkyl substituents and not have any sort of electron withdrawing groups on the nitrogen. You could view that as a carbonyl. If you think about the carbonyl of an amide, this amide actually is going to be not very basic at all because we have this strong electron withdrawing group that also contributes to a resonance change to sp2. And it's really the S character here as well. So since this has the least S character, that means this nitrogen is the least electronegative. That means that whenever we go and protonate this amine, because this would be the product of an acid-base reaction, we end up making a positive charge on the nitrogen. That means that it will be the lowest energy conjugate acid. Whereas in these other cases, if we take something like pyridine, it's sp2 hybridized. So placing the positive charge on the nitrogen actually becomes much worse, only because of the degree of S character. Yeah, I can post these Q&As on Canvas. I've already started recording this. Oh, post it to Canvas? I was posting them to YouTube, and I would just add this on to the Lecture 26 playlist. I can try to start posting them within Canvas as well. I just thought YouTube was a more convenient venue for watching things. Oh, okay, yeah. So I think if you, rather than sending out an email for every single new thing that I post and update, I can do that if that is useful. But I will follow a general trend where I will be putting technically the review class for Lecture 26 in the Lecture 26 playlist and continue down that road. But yeah, you will be able to see this later on. I'll try to put anything that I have. I think I can even get office hours posted online if people want me to do that. I can make an office hour playlist and just keep adding office hours there. They may not be as broken down and nicely formatted as the lectures are, um, but I'm more than happy to go put office hours wherever I can. At this point, the more transparency and the more information that you guys can take in, the better, I would say. Yeah, whenever I post the problem set solutions, I'll post the solutions to the more synthesis practice on the recommended problems page. And does the third structure uh, want the extra proton less or more than the second? So this will be less stable than, let's give these numbers. Call him number 1. Let's call this number 2. Call this number 3. And so let's say number 3 protonated is less stable than number 2 protonated. And that's because this has a more electronegative nitrogen, and electronegative atoms want to hold on to their charge, their lone pair, so they don't want to become positively charged. I have a like and a subscribe. That is great. I'm really progressing into the 21st century. And to kind of round out this problem, now we have this nitrogen that wants to hold on to its electrons. It's chiral. It's sp2 hybridized, and its lone pair is an aromaticity. Something that I didn't mention in the lecture, but if people are curious, I drew in the lecture that we consider, just out of homology to the others, protonating the nitrogen. Turns out, because pyrrole is aromatic, and this kind of follows along the lines of some of the reactivity we've observed in electrophilic aromatic substitution, actually pyrrole likes to protonate at the carbon. So this does not change the logic of our answer at all, but it does allow us to maintain the nitrogen and sp2 hybridization, and we still break aromaticity. So breaking aromaticity, either way you look at it, is going to be a pretty big penalty. And so this is going to be very bad. And along the way, we also posted the pKa's of each of these conjugate acids for reference. And it shows that each of them are about an order of 5 pK units apart from each other, where this is about 0, the middle is around 11, and number 3 would be around 5 or so. So hopefully that clarifies this. If there's any questions about this, that's good. If people want me to go over the other acid-base problem that was on the was actually just below that on the slides, I can do that. Or I can answer a completely different question. So this is something that you can actually correlate. So whenever you have something with a trend of increasing basicity, let's say we are increasing basicity in this direction, this will also correlate to a decrease in conjugate acid acidity. So maybe we can kind of put these in order. So if we put these in order of increasing basicity, we go from the left to the right. These are increasing bases. Now, if we consider their conjugate acids, whichever form of conjugate acid of the pyrrole you want to consider. I'll stay consistent with the N-protonated one. N-protonated one is actually even more acidic, I think. So now we have the piperidinium. This is the least acidic, which means that piperidine is the most basic. So it's the most basic because it is the best at taking a proton. That means the resulting conjugate acid will be the least acidic, it'll be the most stable. In contrast, pyrrole is actually a very poor base, so if it gets protonated, it's actually a pretty good acid, and it really doesn't want to be protonated along the way. So these two concepts are sort of interrelated. Does that correlate to the stability of the molecule? So generally, something that's very acidic will be less stable. So just like how you would say probably like HCl is kind of more reactive and higher energy than something like acetic acid. Cool. And that's why whenever we go and look at stabilities of conjugate acids or bases, if you can evaluate that trend, frequently reflects on the corresponding trend to the neutral molecules. Cool. Do people have any more questions on this? Or any of the other reactions of amines? Or isocyanates? Or reductive amination? I don't know. Have the YouTube videos been working? Yes, cool. One of the days I had meetings all afternoon, so I'm sorry for I had to clear my throat several times. I went and re-recorded some things just in case. Why do you look at the protonated to determine basicity? So if we're thinking about how good a base is, in an acid-base reaction, a base will take a proton. So a lot of times if you look at the product of a reaction, by considering how energetic the product is, it'll give you some idea of how favorable that reaction is. So a very good base will lead to a low energy or very stable conjugate acid. And a lot of times that's useful to kind of look at both so that you can go and compare. Sometimes it'll reinforce trends or it'll help to clarify either a stabilizing effect. Maybe it's a resonance effect or something like you lose aromaticity along the way. That isn't going to be initially apparent by just looking at the starting molecules. Some people can just look at one or the other and get it right. But a lot of times if you can go and compare or consider that process. Yeah, exactly. So frequently if you're looking for what is the best acid, you want to see how stable is the conjugate base. So it goes in both directions. And so you can rationalize something like a carboxylic acid being a very good acid because the conjugate base is stabilized by putting the charge on two oxygens through resonance. Whereas something like an alcohol is going to be less acidic because the conjugate base only puts the negative charge on one oxygen. Yeah. How were you able to distinguish between the level of basicity of 1 and 3? So from hybridization, they're essentially the same. So they're both sp2 hybridized, so they both want to hold on to this lone pair approximately the same amount. Whenever you protonate the pyridine here, it is still aromatic. Because its aromaticity all comes from the double bonds that are within the ring, and it doesn't use this lone pair that is outside the ring. So after it gets protonated, this ends up still being aromatic, whereas whenever you try to protonate pyrrole, it ends up losing its aromaticity. So it either needs to use the pi bonds or the lone pair of the nitrogen that are actually involved in aromatic. Because it's still aromatic, it's just more basic. So it's more or less we're looking at competing factors. If you go from the hybridization level, this is a good start because generally nitrogens with a similar hybridization will have similar basicities. But then we need to go and think about if we use the lone pair in an actual acid-base reaction, does that go and result in any loss of a stabilizing factor? And so this is where actually looking at the reaction is useful because the pyridine remains aromatic. So it's not that it makes it more basic, it makes it as basic as most sp2 hybridized nitrogens. But now we can see that the sp2 hybridized nitrogen in pyrrole is maybe different because it'll have to lose aromaticity in order to participate in an acid-base reaction. To determine whether the lone pair participates in aromaticity, then we can go and consider, essentially you need to be counting the number of electrons. So I think in topic 1, there is a section on aromaticity that kind of shows a variety of heterocycles, including pyridine, pyrrole, and also furan, which is the oxygen analog, which has 2 electrons. And some of this has to do with the geometries. So if you look at the nitrogen in pyridine, this is a flat molecule. So we see we have a double bond, a double bond here, a double bond here, and a double bond here. So this is flat. That means that this nitrogen has to be flat, and this lone pair is actually in the plane of the page, whereas the p orbitals are actually above and below the page. So a lot of aromaticity and resonance has to do with where the orbitals are in space. Here in the case of the nitrogen, this lone pair is, if it were sp3 hybridized, it would be kind of angled out from the pi system. But since there's only 4 electrons in these pi bonds, this lone pair will add 2 more electrons to make it aromatic, and it will rehybridize to become sp2. Kevin asked, what about the case of acidity? Do you mean what about acidity in the context of aromaticity? So this actually can come about somewhat. I'm going to use a different sheet. I'm just going to go to this example and not comment on this right now, just to show you an example of how aromaticity could impact the opposite case of something like acidity. So here we can go and look at something like cyclopentadiene, and let's compare it to an acyclic molecule. Yeah, like a linear analog. So these are 2 different things. So let's consider maybe 2 different protons. Let's consider a proton here and a proton here. If we're going to call this, let's call this 1 and this is 2. This hydrogen of 1 is actually way more acidic than the hydrogen of 2, even though they look quite similar. And this is because after you deprotonate 1, it gains aromaticity. This ends up being a 6-pi aromatic system. It's a charged aromatic system. Whereas here, this does have resonance stabilization, but it's actually going to be very, very difficult to deprotonate to. No aromaticity. So also in the case of acidity, you can have effects of aromaticity, but it's usually the product becoming aromatic. Actually, you could even use the same logic, perhaps, to describe why something like protonated pyrrole is very acidic. That's because if it were to be used as an acid, we would go and regain an aromatic system. I never had my positive charge on pyridinium. Okay, cool. Someone wants to go take a look at the Gabriel synthesis. So I'm just going to quickly sketch out the process. So the Gabriel synthesis involves first we deprotonate phthalimide. We react it with, I'm going to react it with benzyl bromide. It's some sort of alkyl halide. And the phthalimide anion acts as an ammonia equivalent. So if you try to use ammonia directly in reactions, it's actually not very good at making primary amines, unless you use a very, very large excess of it, because it's hard to control the number of alkylation events that'll take place. So this is just an SN2 reaction. But now we end up with this big old phthalimide group on our molecule. We need to get rid of it. And the way people remove it is by using hydrazine. So hydrazine is not just for the Wolff-Kishner reaction. It's also rocket fuel. It's a pretty reactive molecule. It's way more nucleophilic than your average amine. We'll be able to attack this carbonyl directly, both because hydrazine is more nucleophilic than the average amine. And these imides are more reactive than normal amides. Just like how anhydrides are more reactive than esters, imides have one nitrogen lone pair that's kind of shared between two different functional groups here. So this will be able to attack. And this will follow along similar to how we've seen other types of addition-elimination processes, where we had amines attack different types of activated esters. We'll make a tetrahedral intermediate. You can have this tetrahedral intermediate come down. There may have been proton transfers happening along the way. Now let's just say we made an amide anion. I won't ask you guys to do a detailed mechanism of this. Maybe if we had more time. And let's just say we have proton transfers. We end up with one neutral amide. This is actually called a hydrazide. And this nitrogen lone pair here is very nucleophilic still, right? Its electron withdrawing group is further away. And this will be able to do an intramolecular reaction. So it will attack this carbonyl. This makes a 6-membered ring. Which after proton transfers, we would need to make this amine a good leaving group. Exactly how it breaks down, we don't need to worry about. But formation of this final ring is what is going to end up driving it away. Can't stop the ring closure. And so now this kicks out benzylamine. So it's a pretty long process if you try to draw all the steps, and I didn't even draw all the proton transfers. But now this thing that leaves is benzylamine. You get this wacky looking heterocycle as a byproduct. Does that clarify the end of the Gabriel synthesis? Boom. What prevents the molecule? Oh yeah. So the just to clarify, I think this is a question asked earlier. So this is nucleophilic only when it's deprotonated. This nitrogen actually isn't very nucleophilic at all when it's neutral, because it's participating in resonance. The reason this is able to do an alkylation is because it's deprotonated. Since this doesn't have any more NH groups on it, it can't be deprotonated, it can't be alkylated again. Can the end product heterocycle be converted back into phthalide, or does it need a reaction to go again? No, people throw this away. This gets just thrown away. You technically could do it. You would need to do a reaction that you guys don't learn where you would end up reducing this bond and then adding acid. I don't know anyone to actually do that, but you could potentially do this. Got any more questions? Cool. Yeah, we will be having office hours as well tonight and tomorrow night at 5 p.m. That is on meetings. And I can answer more questions as needed. Okay. So we have a question about comparing relative stabilities of esters. Tert-butyl, tert-butanoate. Oh, that's too angry right now. I'll go to a purple, unless this is too hard to see. So I think you're asking about something like this. So stabilities between different things, and then you had methyl methanoate. That actually would be, I think, a formate, technically. There are subtle electronic effects. There are subtle electronic effects between, say, A, B, and C, but they're really too minor probably for us to be trying to think about too hard. Alkyl groups generally will be a bit more electron donating. So you can say that this methyl may donate a bit more than, say, one of these hydrogens. Maybe I'll try those out. But these are really small differences. The differences, if you were talking about the rate of a reaction, though, that would now become quite different where sterics come into play. So A, B, and C, especially A versus the rest, would have very, very different reactivity just because these methyl groups will block everything from trying to come in and attack this carbonyl that's right here. Along the way, when a carbonyl is attacked, it goes to a tetrahedral intermediate that's actually larger in volume that also would kind of increase these steric effects. And then you could potentially rationalize that C may react fastest because it is the least sterically hindered. It also has the least stabilization through something like orbital interactions. We don't talk about much of this hydrogen. Does that answer kind of the question about stability? I probably wouldn't ask a question on relative stabilities. I would probably ask about like reactivities between them. And for these, they would have different reactivities as a result of sterics. If you ended up having electron withdrawing groups, like if you started converting all of these to now fluorines, it would make this carbon more electrophilic. Awesome. Can you relate resonance to basicity? So generally, usually when we're thinking about a base, there's some sort of lone pair, right? So we think about a lone pair. Let's say we have some nitrogen-containing molecule. Whenever we go and now put this lone pair into resonance, let's say we make an amide now, this lone pair wants to actually be in conjugation with these p orbitals that are kind of going up and down on this pi system. So that means it will flatten out. And now this lone pair will be shared across two different atoms. So to this extent, you can relate resonance and basicity, or at least bring them up as a sort of coupled idea. The lone pair that is on its own, not being shared with other things, will be higher in energy. That means it'll be more basic. And this is true if other things are the same. So usually you'd want to make this comparison between two different nitrogens. And usually when we're talking about acidity, we try to stick to usually one type of heteroatom so we can make these rational comparisons. Whereas here in the lone pair on this nitrogen, it wants to go and be in resonance. And we see that now it's losing some of its charge over to the oxygen. It's being spread around. And amides are much less basic than a, say, tertiary amine is. And whenever you protonate an amide, it actually gets protonated on the oxygen because of this resonance, because you want to end up having that positive charge on the nitrogen rather than the oxygen. And also this allows it to maintain resonance of the conjugate acid. Yes, clarity. So good. All right, I think we're rounding out to the end of class. There's no more questions. I'll see some of you at the office hour. Feel free to upload things to get your problem set submitted before class next Wednesday. I've already posted lecture 27, and so on Wednesday we can talk about either that material or material that'll be going more towards the exam. I'll leave it up to the people and the questions they ask. And I'll do my best to have lecture 28 posted before class on Wednesday as well. And that would be discussed on Friday, just that we always I'll try to stay one lecture ahead of schedule. Well, I hope everyone has a good day. Stay healthy, stay happy. Adios.